This is an equilateral triangle, and inside the triangle I've drawn a circle just touching each of the sides, and inside the circle I've drawn this smaller equilateral triangle. Now the problem I'm going to look at is this. What's the area of this small triangle as a proportion of the area of the large one? Well, there's one obvious way of working that out, just using trigonometry, and I'm going to have a go at it. And though it's a fairly obvious method, it's a rather slow one. In the meantime, we'll show you some ideas which will lead to a much smarter way of solving the problem.
Now, the ideas which will help with that problem come from the unit. They're the ideas of classification and equivalence relation. We're going to look at some geometrical examples where these ideas are used, and also at how you write down proofs. So let's start with some geometry. Well, here's an equilateral triangle in the plane. Now, we know if we rotate the plane like this through an angle of 2 pi by 3, the triangle will look as if it's in the same position. And again, after a rotation of an angle 4 pi by 3, it again looks as if it's in the same position. And finally, if we don't rotate the plane at all, then obviously the triangle is in the same position. So these three rotations through angles of 0, 2 pi by 3, and 4 pi by 3 are symmetries of the equilateral triangle. Now, our question is this. Can we sort the points of the plane so that 2 points are in the same subset if you can move from the first point to the second by one of these three rotations? Well, of course we can. We can sort the plane into a whole lot of subsets, and with one exception, each subset will contain precisely 3 points. Now, that was a very easy example, but here's a slightly more complicated one. That equilateral triangle looks as though it's in the same position if you rotate it through one of these angles, but it also looks as though it's in the same position if you flip it about an axis, like this. Well, there are 3 axes we could use, and 3 different flips. So, there are 6 symmetries of the triangle, 3 reflections, which come from flipping the triangle, and 3 rotations, the ones we had before. And again, we can ask our question about the points in the plane. The question now is, can we sort the points of the plane so that 2 points are in the same subset if we can move the first point to the second point by one of these 6 operations? If we start with a point here, we can rotate it by 2 pi over 3 to get this point, and 4 pi over 3 to get this point. We can also reflect it in each axis to get these 3 new points. We get 6 points altogether, and if we take any one of these points, then we can get to any other by applying either a rotation or a reflection. And no matter how many of these rotations and reflections we apply, we can't get any new points. So the subset that we get from this starting point has 6 points in it. This different starting point gives a different subset with 6 points in it. But not all the subsets contain 6 points. If we move the starting point around, then when it's in this position, there are only 3 points in a subset. That's because the starting point is already on one of the axes. So if you reflect it in that axis, it doesn't move. And if you reflect it in one of the other axes, it moves to the same position as if you'd rotated it. So some subsets have 6 points in them, and some only have 3. And of course, the point in the very center of the triangle isn't a subset all on its own. So, once again, we can sort the points of the plane according to this rule. But as you saw in the unit, not every rule can be used for sorting. So, why do these examples work? The reason is that in each case we have an equivalence relation.
Here's the definition of an equivalence relation. It's a set A together with a rule rho relating 2 elements of the set. And we write x rho y to mean that x is related to y. Now the rule has to satisfy 3 important properties. It must be reflexive, symmetric, and transitive, R, S, and T for short. We've given definitions of each of these properties, and we'll look at them in turn. First, the reflexive property. We say that the relation is reflexive if for every element in the set, x is related to x. In other words, every element must be related to itself. For example, in these pictures, we've used arrows to indicate that elements are related. This example is reflexive because every element is related to itself, whereas this one is not reflexive because this element is not related to itself. Now, what about our example with the 6 symmetries of the triangle? Is that reflexive? Well, first, let's identify the set and the rule. The set is the set of points in the plane, and the rule is that the point x is related to the point y if you can move x to y by one of the 6 operations which give a symmetry of the triangle. And then the relation is reflexive. Every point of the plane is related to itself. We just use the 0 rotation, which doesn't move anything at all. To verify the reflexive property, you have to test every element of the set. No exceptions are allowed. But that test is satisfied because the 0 rotation transforms every point to itself. Now, the reflexive property deals with one element of the set at a time. The next property, the symmetric property, deals with 2 elements at a time. We say that the relation is symmetric if for all x and y in the set, if x is related to y, then also y is related to x. In other words, if the relation links x to y, then it must also work in the opposite direction, linking y to x. This is an example of a symmetric relation, whereas this one isn't. Now, that's not to say, of course, that x must always be related to y. We're just saying that if they're related one way, then they must also be related the other. So what about our example? Is that relation symmetric? Suppose x is related to y. Then there's some transformation which takes x to y. Perhaps it's a rotation, say through 2 pi by 3. If you then apply the rotation through 4 pi by 3, you'll take y to x. Or perhaps you could go from x to y by a reflection. If you reflect again in the same axis, you'll take y back to x. Whichever transformation took x to y, we also have one which will take y back to x. How do we know that? It's because each of our transformations has an inverse transformation. The third property, the transitive property, deals with 3 elements of the set at a time. We say that the relation is transitive if for all x, y, and z in the set, if x is related to y and y is related to z, then x is related to z. In other words, if we can go from here to here, and we can go from here to here, then we must always be able to go from here to here directly. This example is transitive, but this one isn't. Now, there's an important point about this definition. We've used 3 symbols, x, y, and z, because those elements might all be different, but they don't have to be. To show that the relation is transitive, you still have to check the definition in the cases when, say, 2 of these are equal. For example, if the set only contained 2 elements, then x, y, and z couldn't all be different. But you'd still have to check, for instance, that if you can go from here to here, and from here to here, that you can go from here to here directly. To be sure that the transitive property holds, you must check all possible choices of x, y, and z. Let's see what this means for our example. For this choice of x, y, and z, x is related to y by rotating by 2 pi by 3, and y is related to z, say by reflecting in this axis. But x is directly related to z by reflecting in this new axis. For this choice of x, y, and z, x is related to y by a reflection, and y is related to z by a different reflection. In this case, x is directly related to z by this rotation. When you combine 2 of these symmetries of the triangle, The result is also one of the symmetries. So for every choice of x, y, and z, if you combine the symmetry relating x to y with the symmetry relating y to z, the result will be a symmetry which relates x to z. So this relation is transitive. Since it's reflexive, symmetric, and transitive, it's an equivalence relation. In fact, you might have realized that these three properties of equivalence relations are closely related to the axioms for a group. In our example, the symmetries of the triangle formed a group, and the reflexive property corresponded to there being an identity operation which keeps everything fixed. The symmetric property corresponded to the existence of inverses, which take you back again. And the transitive property corresponded to the group axiom of closure, that combining two operations in the group always gives you a third operation in the group. Now, this connection between equivalence relations and groups is fascinating, and we'll use it in our next problem. What we're going to do is to look at another example of a relation to see whether it's an equivalence relation. And this time, we'll show you how to write down a proof that these three properties hold.
This is the set of matrices that we asked you to look at in the pre-program work. We've called it H. It's a set of matrices of this special form where little p and little q are real numbers, and we're told that p squared plus q squared must equal 1. Now, we're going to use this collection of matrices to define a relation, and we'll see that it satisfies the three properties R, S, and T, reflexive, symmetric, and transitive, so that it's an equivalence relation. Now, this is the relation that we're going to use. The set will be the set of points in the plane, just like our previous example. But this time, the rule is going to be that two points are related if you can map the first point to the second by matrix multiplication using a matrix from the set H. So, the point with coordinates AB is related to the points with coordinates CD if you can find a matrix from this set so that multiplying it into the column matrix AB gives you the column matrix CD. So that's our relation. Let's just explore it for a moment and see what happens to some typical points in the plane. This matrix is in the set H. If we take P as the point 2, 1, then the matrix maps it to the point 1 minus 2. So P is related to this point. If we change the numbers in the matrix so that it's still in the set H, then we get different points to which P is related. If we were to try all the matrices in the set H, we'd get all the points on this circle centered on the origin. So the point P is related to a point Q if Q lies on this circle. If we'd started with a different point P, we'd get a different circle. The new point P is related to all the points on this new circle. In fact, the relation seems to be sorting the points of the plane into sets, and each set is a circle centered on the origin. Now, if the relation is sorting the plane into non-overlapping subsets, and concentric circles are certainly that, then we'd expect it to be an equivalence relation. In fact, it is, but this time we're going to look in more detail at the proof.
I'm going to look at what you would have to write down to prove that our relation is an equivalence relation. And we'll start with R, the reflexive property, and I'll write out the proof using the skeleton that you've seen in the text. Now, I must start with this line for all points P in our set A, and I must end with this line, which implies that P is related to itself. Now, how to fill in the gap? Well, the relation is defined in terms of the coordinates, so my second line had better be if P has coordinates AB. Now, what I want to show is that I can get from the coordinates of P to the coordinates of P by multiplying by a matrix in our set H. Well, there's an obvious candidate for this matrix. It's the identity matrix, 1, 0, 0, 1. And part of your pre-program work was to show that the identity matrix 1, 0, 0, 1 is indeed a member of our set H. And that really does complete the proof, because I've got from the coordinates of P to the coordinates of P by multiplying by a matrix in the set H. Now you tackle the proof of the other two properties in exactly the same way, and I'll look at the transitive property. Now I must start by saying for all points P, Q and R in our set, if P is related to Q and Q is related to R. And I must end with the line which implies that P is related to R. Now again, to fill in the gap, I use the definition of the relation. Now that tells me, first of all, that I can get from the coordinates of P to the coordinates of Q by multiplying by a matrix which I've called M, which is in our set H. And it also tells me that I can get from the coordinates of Q to the coordinates of R by multiplying by another matrix, N say, which is also in our set H. Now, how can I possibly justify this last line? Well, I have to show that I can get from the coordinates of P directly to the coordinates of R by multiplying by some matrix in our set H. Now I've got to close this gap. Well, I don't want a result involving the coordinates of Q, so I get rid of them by substituting as follows. I get the coordinates of R are n times the coordinates of Q, which in turn are m times the coordinates of P, which gives me that, or writing it another way, coordinates of R are nm times the coordinates of P. Now, what about this matrix nm? Well, n is in our set H, m is in our set H, and the product nm is in our set H because you showed in the pre-program work that H was closed under matrix multiplication. And that is exactly what I want. I have coordinates of R is a matrix in H times the coordinates of P, which does indeed imply that P is related to R. And that's how you'd write down the proof that ρ is transitive. Now, in fact, ρ satisfies all three properties. It's reflexive, symmetric, and transitive, and therefore it's an equivalence relation.
Well, of course, that's what we expected all along. And in fact, you might have guessed from the circles that the matrices in this set are really just rotation matrices in disguise. So, if you remember, a rotation matrix is of this form, where theta is the angle of rotation. So if you put P as cos theta and Q as minus sine theta, then the matrix has the right form to be an element of H. And if we check P squared plus Q squared, then we get cos squared theta plus sine squared theta, and that's certainly 1. So a rotation through any angle theta is an element of the set H. In fact, H is just the set of all rotation matrices, and they define an equivalence relation because they form a group under matrix multiplication. Now, in the rest of this program, we're going to do two more things with this idea of matrices transforming points in the plane and the equivalence relations that we get from them. At the end of the program, we look at a very similar problem to this one, which you've been asked to investigate in the post-program work. We'll show you the pictures of the different transformations you get so that you have a feeling for what's going on when you write out the algebra for yourself. But first, we're going to extend this idea of rotation to other sorts of transformations that you meet in geometry. You see, rotations are rather special. Here are 2 points, P and Q. These points are at a distance 1 apart. If we apply a general matrix transformation, like this one, the image points need not be a distance 1 apart. On the other hand, if we apply a rotation, the distance between the image points will always be 1 unit. Rotations preserve the distances between points. We say that a rotation is a rigid body transformation, because if a body is rigid, it just means that the distances between different points can't change. You can't deform the body. Another name for a rigid body transformation is a congruence. because if you have, say, a triangle and you rotate it, the result is another triangle which is congruent to the first one. But are there any other transformations which are congruences apart from rotations? This transformation is a congruence. It's a reflection in the x-axis. If you take 2 points a certain distance apart, their images will be the same distance apart. If you start with a triangle, its image will be a congruent triangle. In fact, any reflection will give a congruence. This transformation is also a congruence. It takes any point and moves it a fixed amount in a given direction. If you start with 2 points a certain distance apart, their images will be the same distance apart. If you start with a triangle, its image will be a congruent triangle. This is called a translation, and any translation will give a congruence. In fact, the most general congruence is a combination of rotations, reflections, and translations, like this. Now, as you might expect, the set of all combinations of rotations, reflections, and translations also forms a group. And this group has a special name. It's called Euclidean group. And it's given that name because Euclidean geometry is the study of those properties of shapes which are unchanged when you apply a transformation from Euclidean group. Of course, that's a vast subject in its own right, and it's the sort of thing you might go on to study at second level. But for now, let's bear this thought in mind as we go back to the problem that we started the program off with. How'd you get on, Bob?
Well, what I did was I used trigonometry in this triangle and this one and this one, and that enabled me to find all the lengths I needed in order to find the areas of these two triangles.
And what did you get for the areas?
Well, it turned out that the area of the small one was a quarter of the area of the larger one.
I see.
But, as I said at the beginning of the program, there's a much smarter method, and it uses the congruences of Euclidean geometry, which you've just seen. Now, I know that rotations are congruences, so however I rotate this small triangle, I'll get a congruent triangle which has the same area. And if I rotate it to this position, then we can see that the large triangle is made up of 4 triangles, each the size of the small triangle.
Now, as we promised, we'll finish this program by looking at the problem from the post-program work. Once you've seen the pictures, have a go at the algebra and see if you can prove that the relation is an equivalence relation. Once again, we're looking at points in the plane to which you can map a given point using matrices in a certain set. This point P is related to all these points. But it's also related to all these points as well. If the starting point is in a different position, you'll get a different set of points in the plane. If the starting point is up here, this is the set you'll get. And if the starting point is here, you'll get this set, excluding the origin, which is in a set all on its own. So this is quite a different way of classifying points in the plane. We now leave you to prove that it's another example of an equivalence relation.